Jesus.
All right, everybody, let's get started. We are doing a couple sections today. 1.3 is on limits at infinity. Are you guys ready? Okay. So we've looked at doing stuff like 1/x before. We did limit as x goes to 0 of 1/x. Instead, that went to infinity. What happens if we do something like limit as x goes to infinity of 1/x? So let's reason it out. Like, let's say x is 100,000. 1/x is 1/100,000. Maybe let's add a few more zeros. We get 1/100,000,000. And this first one here is 0.000001. This one, if we throw it in a calculator, is, we've got 8 zeros, 7, 8, and then 1. Wait, I might be off by 1. I might have put down 1 too many. X equals, like 100 billion. One over x is getting even smaller. There's a lot of zeros here at this point, blah, 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 blah. I'm not even counting them at this point. What do we think is gonna happen as x goes to infinity? It's going to 0, right? This is getting closer to 0. Same is true with negative infinity. So. If x increases without bound. And f of x. Gets closer and closer. To a value L as this happens. We say. That the limit. As x approaches infinity of f of x. Equals L. We say the same thing about if it decreases. If x decreases without bound. F of x get closer to L. Then the limit as x goes to negative infinity. Of f of x equals L. And conveniently, the limit laws we did last section. Apply to limits at infinity.
Can you roll a little bit up? I just want to take a picture. Okay, thank you.
Sorry, I thought people were done with the top part already, it's been a while.
Just for me to say organized, was the last class 1.2 only, or was it also 1.1?
We did 1.1 and 1.2. The limit laws, I believe, were at 1.2. You learn about what limits are in 1.1. Anyone need this up longer? I'll do an example of how the limit laws real quick. We like if we do the limit as x goes to infinity. 1 over x cubed. I can rewrite this as the limit as x goes to infinity, 1 over x. And cube that, same thing. And one of the limit laws was we could move the limit inside an exponent. Do this. But we just showed this was 0. 0 cubed is 0.
So what happens when it involves decision? The visual,
You can do the limit on the, we can do the limit on top and bottom. And this is, we can do limit as x goes to infinity of 1. Over the limit as x goes to infinity of x. Cubed. But there's no function on top, the top is going to 1. The bottom is going to infinity. And 1 over infinity, it's going to 0. Alright, so that's like an easy setup, let's take a look at a harder one and discuss what goes on here. Do we need this up longer? Okay. What about the limit as x goes to infinity? Let's do like x squared plus 2 over x cubed minus. Let's do plus 7. Now, if I try to do this here, if I plug in infinity. It's always worth trying, plugging it in, see what happens. We end up with infinity over infinity and we don't like that. And we haven't learned a great rule we'll use later on. So something we can do. Is find the highest exponent. Find the term with the highest exponent. And divide top and bottom by it. Since x is going to infinity, x is not zero, it's definitely not zero, so we can divide by something that's not zero. And it doesn't change the value. Does that make sense? So I'll give myself, I'll rewrite this. The highest term is x cubed. So what I'm gonna do, I'm gonna multiply top and bottom by 1 over x cubed. Since x is not equal to 0 as x goes to infinity, we can do this. It's effectively like multiplying by 1. When we do, the top becomes 1 over x plus 2 over x cubed. The bottom becomes 1 plus 7 over x cubed. I'm gonna write this out the long form first, just so you see how the limit laws apply. And then I'll show you like that way you'll probably wanna do it. So we can distribute that limit as x goes to infinity to each thing. And we just got done seeing that this is 0. That's 0 and that's 0. So we end up having 0 on top. And since there's no x in this, the 1 isn't changing, it's just 0 over 1, which is 0. And the way we, a safe way of writing it without all that stuff. I'll rewrite it real quick to illustrate it. Once you've got to that point, rather than breaking it into all this shit, just apply the limit to each one. And the way to show that it's doing 0 is like do an arrow through it going and point it like it's going to 0. This is going to 0, this is going to 0, and that's going to 0. And I could have written that directly over this and you could save yourself a lot of paper, a lot of work. So that's the appropriate way to do that. There is a method. I don't know that it has a name. I like to call it the quick and dirty method. From a teacher I had at UC Merced. And I don't know why he added dirty. Well, maybe because it's not right. You don't really want to do this. Quick and dirty method to check. Don't do this to do the work, but just do this to check. Eliminate all but the highest exponent on top and bottom. I'll give a better explanation of why this works at the end of this section. But like, doing that here, we have limit as x goes to infinity of x squared over, or plus two over x cubed plus seven. This acts like limit as x goes to infinity of x squared over x cubed. We've eliminated that.
Would you move it up?
Yes, I can, thank you. Let me pause. And now we can cancel shit this way. So limit as x goes to infinity of one over x, after we reduce the fraction. And that's zero. I wonder if he still reteaches at Merced. He worked at NASA too. He's an interesting guy. Yeah, fucking sideburns like Wolverine, like fucking full sideburns. That was his favorite setup.
Pencils in his fingers.
They didn't have fucking claws. He just had the sideburns. He had a cool hat. Always wore the same hat. Like, I don't know. I don't know what type of hat it was. I'm gonna have to ask him what type of hat it was. Sure he still has it. I like it good. He came from his own great Facebook afterwards when I was in grad school, like, and talk to him. You guys ready for more? You guys ready to try example on your own? Oh, yeah, let's do it. So find the limit as x goes to negative infinity of 4x² minus, I don't know, let's do 7x plus 16 over 5x minus 1. This is slightly, you have the printed notes, this is slightly different. I just chose a different problem, but has the same setup. About a year ago, I had my wisdom teeth pulled. Yeah, the old man getting his wisdom teeth pulled. And they said get like chocolate protein milk, and I had got that Fairlife, that's just pretty good. Yeah,
I mean, for what it is, it's not too terribly priced
yeah, it's not too bad. It tastes good considering all the protein it is in it.
compared to some of the other brands, some of the other like extra shit people put into it. It's actually
Actually
not that
tastes like
bad.
chocolate milk, yeah.
Mhm.
You know, one more minute, then we'll do it together, so people are still. Hand in hand moving, so they're working on it. Feels like top one has such a nice, easy start to it. Top two and top three, you're just like. Someone pushed to shove you in the deep end off the fucking high dive. You can just go straight into hard shit, there's no fucking. Cause you already know the basic calculus, you'll by that point. And you're just doing harder stuff in calculus. Alright, so. There's infinities on top and bottom if we do it as is, so what we're gonna do is look for the highest exponent. And it looks like x squared, so I'm gonna multiply top and bottom by 1/x². And this becomes limit as x goes to negative infinity. 4 minus 7/x plus 16/x². All over 5/x minus 1/x². So this goes to 0, this goes to 0, this is going to 0, this is going to 0. We're approaching 4/0, which is like, this blows up to infinity. If that's a little awkward for you, multiply it by a slightly smaller one. If I do 1/x rather than 1/x², I'm gonna rewind this a little bit. If I multiply by 1/x. You'll see that we have the limit as x goes to negative infinity. 4x. I think I lost a sign in there by doing that. I did lose a sign in there, I think. This goes to 4x minus 7 plus 16/x. And this goes to 5 minus 1/x. I did lose a sign in there.
The 5.
This bottom is going to be negative. This bottom is like approaching -0 is the problem. So this way is probably the easier way to do it. When you see it, when you plug it in, well, that's going to 0, that's going to 0. The top is just going to negative infinity, right? That ends up being negative infinity, got a negative in there. So it's probably a little easier to do the slightly smaller one. So I'm gonna revise what I said earlier. Don't divide by the highest power, divide by the highest term in the denominator. Is a more accurate approach. And that's what I had written down in my notes, and I got carried away with what I was saying and just fucking ran with it. Cause it was already the highest term on the example I was looking at. This is what you wanna do. My bad. If we take a look at this with the quick and dirty. QD, quick and dirty. This breaks down, the limit as x goes to negative infinity. We cancel everything out but the highest term on top and bottom. We can cancel negative, or we can cancel on X. And so this is going to negative infinity. When X is going to negative infinity, you really gotta pay attention to. What's going on here, so like. Let me expand on that a little bit. If n is greater than, the following is for like if n is greater than 0. The limit as x goes to infinity. For x to the n. Equals infinity. For all n. This might be a new notation for you, and it probably is. This means for all. That's math symbology. They say for all a lot in proofs and stuff, and they finally like, let's shorten that shit down. So as long as n is bigger than 0, it doesn't matter what x is getting larger and larger. We could have, this is n equals 1/10, the 10th root of x. It's still, as x gets larger and larger and larger, even though we're taking the root of it, it's still getting larger and larger and larger as it's approaching infinity. But. Same requirements, limit as x goes to infinity of negative, or x to the net. Sorry, limit as x goes to negative infinity of x to the n. This is doing two things. This is doing negative infinity if n is odd. And positive infinity if n is even. Because like squaring it cancels out the negative sign. That stems from. A negative number raised to an even power. It's positive. Right, you guys ready for the next part? Who's having fun?
People still sleep.
Maybe, depends on what they're dreaming about. You know what would be really awesome, what would truly make this like a radical time?
If we could sleep while we walked or something.
No, that's dangerous. That's very dangerous. If we added radicals,
Oh, you're talking about that.
they're very much talking about that. You like math, you came and did math on Saturday with me,
That's because I needed to. The future.
yeah. Long-term goals. You don't wanna be the intern, you wanna be the boss one day. Right? Alright, you guys ready? Look like they're doing anything there, so let's keep going. When we have radicals like the following. And I'm gonna do negative infinity on this one. So the. Path to success, let's call it. With radicals. And you're wanting to divide out by something to kind of clear it up. If x is approaching infinity. Divide by. Absolute value of x, which is the square root of x squared. That's one of the definitions of square root of x squared.
Does the infinity matter positive or negative?
It does.
Okay.
If x is going to negative infinity. We can do the same thing. Or divide by negative x if you're not working with radical. And the reason why we can do that last one, recall that the absolute value of x equals x if x is greater than 0, and it equals negative x if x is less than 0. That's the definition of the absolute value of x. Like the absolute value of -2 equals -2, which is +2. It looks weird seeing negative x, but that's really what's going on. Adding the negative there cancels the negative you have there, and you end up with a positive number. So I'll seal that off. We're going to negative infinity, so I'm gonna multiply. Top and bottom by 1 over the absolute value of x cubed. And I'm gonna use them separately in 2 different ways. On the top. I'm gonna use that as the radical. So
That's a negative infinity, or is that just infinity?
what?
The one to the left, the blue one, that's a negative
It's
infinity.
negative.
Okay.
It hasn't changed. So we're dividing by. Like x squared and it's getting cubed. And then we got the radical. On the bottom, I'm gonna use the negative x version. Yeah. So this is why. On the radical, now we can combine the radicals.
Would it be negative x cubed minus x? Because you also had a word. Or just
What?
like right there in the second one and the one in the middle, yeah. So you multiply it all the way.
The +1 is there, yeah,
Yeah.
I think that's what you were asking.
Yeah.
So now the top, we put the radicals together. And the bottom, I can actually do the division, x cubed over negative x cubed is -1. And I got -1 over x cubed.
Mr. Jones, how did you get the second line, the one under the. The second one right there, yeah,
This,
yeah,
so if we treat the absolute value as square root of x squared. This is like x to the 2/2. Then I cube it. This ends up multiplying.
Okay,
So we have x to the 6/2, and rather than writing that as x cubed, which we could. I'm gonna write that as the square root of x to the 6th. Because the whole point of this was addressing the high exponent in here.
yeah,
I'm glad you asked. Wasn't sure if it was entirely clear, it was clear in my head, but like. Alright, so the top. Reduces. We've got the square root of 9. Minus. 1/x to the 5th. And on the bottom, we have -1 minus 1/x cubed.
Since it's going to negative infinity, can we just call 1/x over 5/0 and bring out a 3 from the?
That's where we're going. So to save yourself a bunch of writing, remember the limit laws allow us to move stuff inside like an exponent. And square root is really something to the 1/2. So I can do the limit on the outside, or I can move the limit onto the inside. Since it's power. And if I move the limit on the inside, now we can apply it directly to the 1/x to the 5th. We can say that's going to 0. We can do the same thing on the bottom, that's going to 0. And this is headed to -3. We've got +3 on top, -1 on bottom. Which equals -3. Is that not everything you hoped it would be? But wait, there's more with radicals, more fun time with radicals. You guys ready for more fun time with radicals? Why not? Radicals are such a, pain in the ass. But if you can have fun with them, then they're less of a pain in the ass. Does anyone need, I see a couple pins in the middle, be patient. Everyone good? Alright. Fun time with radicals. Limit as x goes to infinity. The square root of x squared plus 3. Plus x. And let's make that negative infinity. I wanna go to negative infinity. This is a stupid problem if it's positive infinity. It's really easy if it's positive infinity. Like, we can separate this, and it's handy to separate this, so you see a little bit better what's going on. If I stick in negative infinity to the first one, it gets squared and becomes positive infinity. Like positive infinity squared, and then I take the square root, this whole thing is like infinity. If I stick in negative infinity, this is plus negative infinity. So I have like an infinity minus infinity situation. And you may be inclined to say anything minus itself is 0. doesn't apply to infinities because some things are going to infinity faster than others, so it might be a bigger infinity. Which seems weird. But infinity is not like really a number, it's a concept, they're not numbers. So this is like an uh-oh situation. Or Scooby-Doo style ruh-roh. I like ruh-roh, that's bad. So what can we do about this? What we're gonna do is multiply by the conjugate. And we're gonna do it on top and bottom. If I do that, the top. This is like A plus B, A minus B. On top, so this is gonna be like difference of squares. I will have x squared plus 3 squared. Minus x squared. And on bottom, I still just have what I had. Alright. We clean up the top. Notice that I keep rewriting the limit every time. Don't like drop it to save you, you're not saving yourself a whole lot of writing by doing it. But if you drop it early on and go all at it later. Well, you probably will forget once in a while, and now you've actually made it so it's technically wrong on paper. Because by not showing the limit, you're saying that the limit's done. You wanna keep showing the limit until you've done, you're done evaluating it. It's a pain in the ass, I know. That one is x squared plus 3 minus x squared. And so when we clean up the top. We just have 3 on top. So what's going on bottom? Negative infinity is getting squared and square rooted, so this is gonna be like a positive infinity. And then we're subtracting. X, but x is going to like a negative infinity. So we got like a plus and a plus. So it's like just infinity still. So this is like going towards 3 over infinity, which is 0. Wake up. Wakey, wakey. You want me to turn on the light? That'll help. So like, and as we saw this earlier in the previous section, when you see radicals and something's being added or subtracted to it. Like one of the go-tos has just been like conjugate. Hit it with a conjugate. It can't hurt to try. And it might just lead to success. Some of these things you'll, some of the problems, it's trial and error, figuring out what to do. So try different things and we're showing you tools in the toolbox. What's going on with that quick and dirty thing? So this is like, since, and this is only like for limit as x goes to positive or negative infinity. You gotta pay attention to that, this, you don't really wanna do it otherwise. Like. We're now at this point, we're looking at end behavior for polynomials. End behavior means what's happening at the ends of the graphs or at infinities. So like, let's say I have some polynomial. I don't know, we'll call it C0 plus C1x plus C2x squared. Plus C3x cubed plus dot dot dot. Cn minus one x to the n minus one. Plus Cn x to the n. Written in backwards order. Normally we write the largest polynomial first. We can see what happens if we like, since we're going to positive or negative infinity. We can factor out an x to the n. On bottom. So like what I'm gonna do. I don't wanna do this. No, I'm gonna factor it out on top. Limit as x goes to positive infinity, like pull out an x to the n. This is like C0. Not, that's x to the n, there we go, x to the n. Plus C1 over x to the n minus one. Plus C2. X to the n minus two. Plus C3 x to the n minus three. Plus Cn minus one over x plus Cn.
So, I mean, for infinity at least, for when the limit, when x goes to infinity, positive or negative, as long as there's an x at the bottom, so this would work for that infinity.
Yeah, the idea is, we're kind of like. We're showing like ignoring this part, ignore that. If we applied it to this is going to zero, this is going to zero, this is going to zero. All of these are going to zero, this one stays. So the highest exponent in a polynomial. Dominates end behavior. And I'll just point out an example. If you compare. X to the sixth and. X to the sixth plus. X squared. And we do something really large, like let X equal 1,000,000. I've got 1,000,000 is 6 zeros. I've got 10 to the 6 raised to the 6th power. So 10 to the 36. Damn, that's a big number. Here I've got 10 to the 6 to the 36. Plus 10 to the 6, not 36, 6 there. 10 to the 36 has 36 fucking zeros. I wrote 16. This only has 12. It's like counting pennies when you have millions of dollars. You don't give a fuck about the chump change when you've got, millions of dollars. pennies are obsolete, dollars are obsolete, hundreds are obsolete. When you have a bank account that's got like $70 million, you don't give a fuck about $1,000, it's meaningless, it's chump change.
What's that one?
What?
10 to the 6 plus 10 to the what?
10 to this, I keep doing this, I get 6 in the wrong spot. I'm replacing this X with the 10 to the 6. So I plugged in 1 million into each of those. The top, this one's super big, this one's a little bit bigger,
So that's 10 to the 36 and that's 10 to the 12.
yeah. Like looking at it, maybe I shouldn't have used X to the 6. Maybe I don't even need to use 1 million, let's just do 100. If I did X equals 100, we've got. X to the 6 is 1 0 0 0 0 0 0 0 0 2 3 4 5 6. X to the 6 plus X squared. That's what adding in the X squared is at 100. This is millions, billions, trillions. 1 trillion versus 1,010,000,000. If you've got $1 trillion, 10,000 is nothing. So that's like how the largest polynomial dominates that behavior. Let's take a break. Sorry, I meant to take a break earlier, but I was just using an example that took longer than I thought.
That's a 1, or that's it's supposed to be 0?
Where
Below the x to the power 6 plus x squared.
equals 1 and then a bunch of zeros. And then a 0 1 0.
Okay.
Like, if you want, plug it into your calculator, 100 to the 6 plus 100 squared. That's probably the quicker way than me writing it out by hand,
Plug it in a bank account.
right?